Hello everyone, welcome to Aspen Plus tutorial video. Today I'm going to talk about pitch analysis, heat exchanger design, heat exchanger network, and things like that using Aspen Plus Energy Analyzer. Now, because the topic is quite, I would say, lengthy, I decided to divide the YouTube videos into three parts. The first part is we just simply go through the interface of the Aspen Energy Analyzer software itself, and then we're going to construct a simple four-stream hot and cold composite curve, and then it's going to analyze what is the potential heat transfer or potential energy that we can extract from those two streams, as well as compare what would be the cooling and heating energy requirement. Let's say when we change our delta T minimum from say 5 to 10 or 20, things like that. Okay, that's the first part of the three part videos that I'm going to upload later on, including today. And then on the second part of the videos, once we have the idea, the working, the interface of the software, we can then construct a heat exchanger network. We will try to learn how to add heat exchangers and create a simple design. And then on the third examples, we can do a more, I would say, detailed and then slightly more complicated design, and then maybe analyze from the economics point of view and stuff like that. All right. So for the first part, let's begin. See, okay, before that, because when people talk about heat integration, people always talk about pitch analysis. I'll try to find what's the best, I would say, definition, I guess. What would be the best, I would say, description of what does it mean by pitch analysis? I know there's a lot of textbook available, they have their own version, but I think this one, the one that I take from this Brannan Rules of Thumb, published in 20, I don't really remember what would be the published years from this book, but this is on the fifth. This is the fifth edition by Stephen Hall. So he provided a rather interesting, I would say, discussion on what does it mean to have a to what does it mean? What does pitch analysis mean? So it is a method. It's a systematic, I would say, guideline or method that helps you to optimize energy usage from your plant. Now, how can we optimize energy usage? When we want to optimize energy usage, we pretty much want to minimize, the cooling requirement, heating requirement, and stuff like that. Of course, it also involves money, so I want to reduce money because heating and cooling duty is basically directly relates to the money, the cost requirement to run the plant. So how can we do that? So according to this textbook, right, the first thing that we need to do is first we need to analyze our heat flow. So how can we do that? To analyze our heat flows, first things first is we need to know what is our process. That's where PFD and then heat and material balance come to pictures. Where let's say stream A, we need to is being heated from, let's say, temperature A to temperature B, and then stream number 4 need to be cooled down from temperature C to D and stuff like that. You are dealing with many stream, and they have different heat capacity. They also have a different cooling requirement and heating requirement. The first things first, you need to understand your process as well as you analyze what is the heat requirement. Analyze heat flow. So is it does heat flowing in or does heat flowing out? So heat flowing out is pretty much is being cooled down, and then vice versa. So from there you can figure out what would be the maximum recovery potential. From there from there the next step is to establish energy target. So in this case, right, you need to decide what would be the best target for what would be the best uh, or most practical cooling and heat duty requirement that is needed. In the textbook, right? Later I will give you the textbook that I always refer to. In the textbook, maybe for the plant that is being I would say developed like 60 or 70 years back, to do heat integration, when you do a pinch analysis, do heat integration, and then apply them to a plant, you can have a pretty significant amount of energy recovery, so which is good, but then considering that these days we have a very, I would say, smart plant, and then the plant has been designed, with a lot of advanced software. They have a lot do a lot of studies and stuff like that. I mean, to have maybe like a 10% improvement in energy usage is quite rare. But anyway, we should learn how to do pinch analysis, maybe to have like a 1 or 2% improvement. Um, so this is why you need to establish your own heating and cooling duty requirement, because So how does that? What does that mean? So how can we control that? So to control that is pretty much we need to figure out what is our minimum approach temperature, or delta T the minimum temperature difference between hot stream and cold stream. So it can be 5, 10, 20, depending on the situation, depending on the process stream and stuff like that. And of course, after that, after you have identified those things, you have developed your own curves and stuff like that. This is where you need to identify efficiency. Maybe you found out that, okay, after you do the analysis, you found out that the current plant does not have heat exchangers. We should put heat exchangers to exchange heat from stream A to stream B, stream C to stream D, stuff like that. And then what does it mean by defined process improvement? And one, you add heat exchangers, you design it to ensure that the energy usage, overall energy usage, is kept at the lowest value possible. Well, it must be practical. It must be practical as well. I think if you see the one in the yellow text box, right? I think the last sentence really captured my eye, because eventually, when you have all of this methodology, right? Eventually, it is up to the engineer to decide whether you whether you want to proceed with the improvement or not. Maybe because you have some issue. Maybe in real life you have some issues. For example, say for example, a stream one cannot be exchanged heat from stream B, even though in theory it can be done. Maybe because there's not enough space to put a line, or maybe those particular stream has a very uh, corrosive, I would say, properties. If you decide to do heat exchange from with string number 4 to 5, right, explosion can occur, or maybe your boss simply does not really want to have that heat exchanger because of, I don't know, some weird reason. So eventually, after you do analysis, they might be some, I would say, unknown that cannot be put into the pinch analysis. But you as an engineer need to, given the ideal case, you also need to figure out. You also need to take information from from real case, and then decide whether should I go with this design, or is there a possibility for me to change the design based on the process required. No, based on the constraint that are available. Maybe because of the money, right? Maybe your boss said that, okay, the ideal design should have 5 heat exchangers, but your boss said, okay, we can only have 4 heat exchangers. So how can we take into consideration that when you design heat exchanger network? All right, I think that's quite long, I would say, discussion on what does it mean to, what does pinch analysis mean. Um, so let's move on to the next slide. But anyway, so there's a lot of way for you to do pinch analysis. The what is called the low tech one is the graphical abstract problem table method and stuff like that. But in this case, we can use a software, Aspen Energy Analyzer, because it make our life a lot easier, I would say. So let's check out our software. So as you can see here, this is the print screen of my Aspen Plus Energy Analyzer. I'm using version 12.1. If you use a, a more recent version, they are not much different. And then if you see on the figure below that, you will see that example of heat exchanger network utilizing a 3 stream and three stream, two cold stream, and then one hot stream, and then we have one cold utility stream as well as hot utility stream. So you can do a lot of stuff. But this is pretty much the one on the figure pretty much shows you what's the interface looks like. But we're gonna explore that one later. But anyway, if you know, Aspen has a lot of family of software. They have Aspen Plus, Aspen HYSYS, Aspen EDR, Aspen Custom Modeler, Aspen Absorption, Aspen Batch Process, and of course, this is the one of their many family of product, Aspen Energy Analyzer. So it is an energy management software, just for you to analyze the heat to analyze your process, and then to design a heat exchanger network, and then if you have the existing network, how can you improve it further and stuff like that. So they have two modes of, I would say, I'm not saying calculation. They have, you can use this from two modes. Okay, the first one is just from the design mode, where you just simply design your network, and then they're gonna spit out the output, and then along with other information. And then operation point of view, I will explain later. So the good thing about Aspen is that Aspen Energy Analyzer has been integrated within the Aspen Plus. But in this case, I'm gonna use Aspen Energy Analyzer as a standalone software. But as I told you earlier, it has already been integrated within Aspen Plus. It's kind of like similar to integrated economic in Aspen Plus. So you can simply open Aspen Plus. After you run your simulation, you can go to the Aspen Energy environment. You can do whatever you want. Same thing like this. But I felt that the standalone software is more easy. It's a lot easier to work with. Yeah, as I told you earlier, the first mode is design mode. The second mode is basically operation modes. Basically, what does it mean here is, let's say you have your heat exchanger network, and then you want to figure out how well, or what is the actual, I would say, performance of your network compared to the ideal one, in the case where you have a fouling issues, when you have one heat exchangers being removed and stuff like that. So it kind of consider the operation part of your heat exchanger network when you run the plant itself. Of course, among the important part here is for you to determine what's the size, like what is the heat exchange requirement, and of course the cost, and then the operating cost, capital cost when you add new unit. What is the is it getting worse, or is it getting better economically and stuff like that? But I don't really recommend you to use the cost provided as per the energy analyzer as the absolute cost for you to report, because I think the best way is for you to just simply use that as a relative comparison with the base case. Let's say the base case giving you like a 1 million utility usage, and then the other one, after you hit exchange network, it become like a 50% lower. So it's better to have a relative comparison as opposed to providing absolute number and then give so that because I think this one, for the costing, it's better for you to use the economic evaluation within Aspen Plus as opposed to use whatever in here, because the one in Aspen Plus is more comprehensive. But as I said, it will give you it will give you some values, monetary values which you can refer to. But then again, as I said, it's better for you to use them for comparison purposes only, but not for not as absolute number. Let's see. Okay, the figures on the top right is just how it looks like on the PFD, and then how it looks like on the heat exchange network is on the bottom left, bottom right, where you have all of the nodes there representing the heat exchangers, and then the one with the red nodes is basically the heat exchangers utilizing the hot utility. In this case, the hot utility is around 1000. It's probably a hot air or something like that, or basically a furnace. So of course, this is the one that we're gonna do later in part number 2. Part 1, we're just gonna go over the basic, I would say, interface of the software, and then we're gonna do a pinch analysis, and we're gonna draw a TH diagram. All right, moving on. So what is our design problem? It's quite simple. Our design problem, let's see. So we have, in the figure, we have a four stream. Uh, it is a grid diagram or four stream. We have a two hot stream and a two cold stream. One need to be cooled down from 170 to 60, and then one need to be cooled down from 150 to 30, and then one need to be heated up from 20 to 135, and another one need to be heated up from 80 to 140. And then, of course, what is our task here is quite simple. Just create a hot composite curve and then a cool composite curve to extract the energy from the stream. We're going to use a cooling water default condition in the software as our cold utility as well as high pressure steam. Default condition as our hot utility. And if you see on the table here, right? You have the CP value. This is the big CP, by the way, means that M multiplied by CP, mass multiplied by specific capacity. This one is a big CP. What does it mean? Is it is a heat capacity flow rate. Uh, I don't know whether that makes sense or not, but big CP here is equal to mass time specific heat capacity. And delta H is here is basically amount of heat that need to be removed or added. It's basically a CP multiplied by temperature difference. It is as simple as that. And so what we need to do in our design problem here is number one, we're going to construct a composite curve when we use a temperature minimum what is it called? When we use a pinch temperature of 5 degrees Celsius, and then the other one is 10 degrees Celsius, and then we're just going to simply compare what's the heating and cooling duty requirement. Um, for those who don't know what is the composite curve, it is basically a it is a TH diagram. Okay, it is basically a line that combines all of the hot stream that represent all of the hot stream in the TH diagram. And then that is called hot composite curve. And then cold composite curve is basically a single curve that represent all of the cold stream in the TH diagram. T here means temperature on the y-axis, and then H here is enthalpy or heat, if you will, on x-axis. As simple as that. And for your information, this example problem, you can refer to a textbook by INC Cam. Title is a pinch analysis and process integration. I refer these textbooks a lot. It's quite simple to follow. I think this one is on chapter 2, example problem 2.4, if I'm not mistaken. I could be wrong though, but please please check. So anyway, let's go to, okay, to construct those diagram, we need to go to Aspen Energy Analyzer. All right, let's go. All right, everyone. All right, everyone. As you can see here, this is the interface of my Aspen Energy Analyzer. All right, first things first, on the top right, on the top left, you will see there's a file here where you can pretty much click new, open a new file, save as, and stuff like that. And maybe you can open the latest one. That is pretty much the purpose of the file button. And then on the edit button, of course, we don't have anything else. It's basically a cut, copy, and paste, but it's not yet active because we haven't opened any file yet. And then in the manager here, you will see this is called Heat Integration Manager. It's basically, if you click this thing will pop up. It's like a window that shows you what is the within the file, okay, within the new file, you will have a lot of like cases. So in this case, you will see uh, you have HI case, meaning that heat integration case. Or like what is heat integration case here means like, okay, what is the specific, I would say, process or heat exchanger process or condition that you want to do heat exchanger network. And then HI, and then you can click. You can also add if you want. So if you click add, I don't know. If you click add here, you will see you will be redirected to this folder, to this window where you need to include the what is it called? You need to include all of your hot stream and then cold stream information. Okay, as you can see here, this is case one where when you click HI case and then you click add, you are creating a new case, heat exchanger, heat integration case, okay, for you to analyze. All right, and then you can close. And of course, this one is to display everything, basically including heat exchanger, heat integration case, as well as heat integration project. So heat integration project, you can also add. Okay, what is the difference between heat exchange heat integration case versus integration project? Is just that heat integration case allows you to design or to evaluate only one case of heat exchange, one scenario, okay, one scenario of stream. Okay, one scenario of stream. In our case, we have one scenario where we have four stream that need to be, in which two need to be cooled up, cooled down, and then another two need to be heated up. Only one case or one scenario, if you will. Now, if you choose a heat exchange, heat integration, I keep messing up heat integration and then heat exchange. I'm sorry. If you choose heat integration project, within the heat integration project, I would say heat integration project, you can have multiple scenario. As you can see here, you have a scenario one. So you can also have, and then and then you can do, you have the design one and the scenario one. You can also you can also add, okay, let's see, let me click correctly. Under heat integration project, you can also add scenario. So let's say I write down scenario 2 and I hit enter. So you can see another scenario. So under scenario 2, you can also include, as you can see below here, you will see that under scenario 2, you will need to include a new case. All right, a new case here means a new, I'll say, process parameter. All right, and in the scenario 2, you can have like a multiple design. You can have, as you can see here, I haven't done anything yet, but what I would like to mention here is that under heat integration case, you can only evaluate one scenario, one, I'll say, one stream scenario. If you will. It can be a two stream or four stream, whatever stream. It is basically a scenario here means what is the process condition that you would like to investigate. And then of course, if you choose heat integration project, you can have multiple scenario, you can have more than one scenario, and then for each scenario, you can have your own heat exchanger network design. You can have more than one. As you can see here, you have for scenario one, you have design one. You can also clone the design. Let's say you write down a design two, for example. So under the same scenario, you can have multiple heat exchanger design. We will go over this later, but that is the difference between what is it called? Heat exchanger, uh, heat integration case and heat integration project. All right, but both requires you to first input the process condition. All right, I'm going to close this. So if you see heat integration manager here, let's say I close this one first. If you go here to heat integration, into the manager, if you click the manager, click heat integration manager. Right now under heat integration project, you have one project because we already add one, and then heat integration case, you have case one because you add one just now, and then all heat integration is basically they displaying all the cases and and as well as project. Now, of course, this is like a file or a scenario which you can delete. Okay, just click delete, and then they're gonna ask you whether you are sure to delete or not. So click yes if you would like to delete. If click no if you decide not to delete. So this also the same. HIP1 is heat integration project one. I'm gonna delete. So there is one way for you to create a new heat integration project or case within the same file. All right. But before that, let me show you how to create a new file. Okay, click file here, click new. Okay, let's say I click I'll say no. All right, as you can see, I have created a new file. All right. Within this new file, you can create multiple cases, multiple project. Okay. The first thing first is you have to create a file, and then you can click under managers. You can click hit integration managers to create a new file or a new case or a new project. That's one way. All right. Another way I will explain later. Okay, let's go over the menu ribbon. Under features here, also the same purpose where under features you can click hit integration case. Okay, when you click hit integration case, as you can see, they will redirect you to this process stream specification, I'll say window where you first need to input your process stream information. I'm going to close this. Same goes with the HI project, heat integration project. So you have two methods here to input your heat integration case or project. The first one here is from the manager. The second one here is from features. But if you remember just now, I already created one. So I go here. Now I have case one. I'm going to delete it. So click yes. I'm going to close this window. Now, under tools here, you have a script manager. It's like a script that store all of your property method, all of your process information. If you decide to export or import or whatever stuff like that. Window, nothing much. And then help button. If you click about Aspen Energy Analyzer, is very useful, especially when you would like to know what's the definition, how things work. If you want to add something, this is kind of like your manual help manual, software help manual. In case there are something that you don't know how to proceed, for example, they have a very comprehensive, I would say, comprehensive, I would say, description, procedures, what's the theory that they use and stuff like that in their help manual. All right, in this case, these are new case. Okay, as I mentioned to you, you can create case from the HI manager. You can also create HI case from features. You can also click HI case by clicking this icon. These are just open case, save case. You can also click here. This is a icon version of the heat integration manager. This is the icon version of feature, I would say, menu ribbon. Either one is fine. But in our case, we only have one scenario. So I'm gonna click heat integration case. So I'm gonna click here. I'm gonna click heat integration case. So as I said before, this is what this is gonna pop up first, where you need to specify your process condition. But before that, let me show you. Okay, this is on the first column. You need to specify name, inlet temperature, outlet temperature. MCP here is your big CP. All right, enthalpy, segment, later heat transfer coefficient, flow rate, blah blah blah, and stuff like that. Now in Aspen Analyzer, you only need to provide three information only. Technically four. The first one is name, stream name. The second one is temperature inlet, temperature outlet, and big CP or MCP. Or name, temperature one, temperature two, and enthalpy. Because if you give one of those information, you will get MCP, or if you provide MCP, you will get H automatically. The rest, later I will show you how to adjust and stuff like that. Okay, in this case, data transfer from Aspen HYSYS, we don't have this option. Um, basic because this is a standalone software. But if you want to do data transfer, you can just simply use Aspen HYSYS or Aspen Plus. This one is again data transfer from Aspen Plus. They don't have this option anymore. So because they have the Aspen Energy Analyzer embedded within Aspen Plus. So what I'm showing you right now is just a what is it called? It's just a standalone software because I feel that it is much easier to go about this software. So I'm going to close it. Now, you can also, so as I said before, the first thing that you need to provide is the stream information. Now, in our case, in our example design problem, we only have to provide four stream information, so it's quite simple. So what if you have like 1,000, or maybe okay, 1,000 is a bit excessive, I would say, maybe like a 50. So you can do manually if you want, or maybe you have a certain you already have Excel file, right? For you to import those information, you can do that. You can click here. They will they will find where when you click here, you can import your stream information from Excel to Aspen Energy Analyzer. All right. But you have to remember that to do that, your Excel file must follow a specific formatting for the rows and column. I recommend you to check the help menu to see what is the actual what is the actual formatting for the Excel for you to correctly transfer the information or import the information from Excel to Aspen. All right. The next icon here is a target view. Okay, target here means the utility target for your I don't know the utility. No, target here is but okay, Aspen has many definition when it comes to target. I checked the help menu. One of the things target according to their definition is the ideal version of it, ideal version of the heat exchange. I know it doesn't make sense, but later, maybe if I show you example, later you'll figure out what does it mean. One important thing here, you have a DT minimum. This is the minimum temperature uh, from hot stream, between hot stream and cold stream. You can change from whatever temperature that you want, but the default one is 10 degrees Celsius. Later we'll try to figure out. Later we'll try to change something. And then of course here you can open the composite curve. So this is what we want to make actually. We want to do a composite curve, hot composite curve as well as cold composite curve. On the y-axis you have a temperature, on the x-axis you have an enthalpy or Q or whatever. It's still in the kilowatt, kilojoule, whatever unit that you want. And then this one is a grand composite curve. I haven't read much about heat exchanger network and then pinch analysis. So I will keep this one for later explanation, I guess, once I have done my reading. Okay, but I think this one is more of a when you want to do a utility allocation, when you have like a multiple utility. But this one later, we do a simple one first. And then this one is open utility composite curve. Just a different curve, same thing. But bottom line here is you have all of these icon to show to give you the I'll say the curve that you want and the curve that are important for your analysis. And then lastly here, open hand grid diagram is a grid diagram in Aspen Plus is basically a stream as well as utility stream that has temperature that has all of the stream as well as utility stream, as well as their temperature inlet and outlet represented, in a vertical, in the horizontal line in a single diagram. Later, I will show you what do I mean by that. All right, so the first things first, as I said before, we need to specify our process stream. The first stream is a hot stream, so I'm gonna name it as a H1. Okay, stream hot. Now, if you hit enter, they will go to the inlet temperature. Inlet temperature is 170. It need to be cooled down from 170 to 60. You hit enter, they will go to the next column, 60. And then you have option whether you want to specify MCP or enthalpy. If you specify enthalpy, which is 330, if you refer to the slide, MCP will be calculated automatically. But in this case, I'm going to write down MCP, which is the big CP. It is around 3 kilowatt per Celsius. So I'm going to write down 3000 uh, watt per Celsius. All right. Now, as you can see, they are automatically calculated. Now, HTC, you can manually edit following the specification that you have. But in this case, I'm going to keep it default. HTC is a heat transfer coefficient. The rest is not really that important because it's being it's being embedded in the enthalpy and MCP. Okay, this one is done, and then you click here H2. Oops, H2. All right. The second hot stream to be cooled down from 150 Celsius to 30 Celsius. MCP is 1,500 watt per Celsius. All right. The rest is done, and then the next one is a cold stream. C1. Oops. Okay, it needs to be heated up from 20 to 135. Okay, my CP is 2000 watt per Celsius. And then the last one is C2, cold stream 2. It need to be cooled down it need to be heated up from 80 to 140. And then my CP is 4000 watt per Celsius. Now, this one is done. As you can see, they will determine whether it's a hot stream or cold stream. The red one going down is hot stream. Hot stream, by definition, is a hot stream that need to be cooled down. The temperature need to be lowered from temperature 1 to temperature 2. Cold stream by definition, is a stream that need to be in which the temperature need to be raised up from lower temperature to a higher temperature. So that's the definition. Okay, maybe you are wondering, let's say you have a typo, right? Let's say you do a wrong. How do you want to delete a wrong information? Let's say you write down like a C2, no, C3 from 100, right? Let's say you accidentally put this information. How can you delete? It's quite simple. You just click here, you left click here, and then you click, you press delete button, okay? And then you click yes. Okay, now we have specified our process stream. Now, you might be wondering, okay, the one that you learn from the university or from the class is you, uh, between this temperature range, you assume that MCP or CP is always constant. Um, Okay, if it's at the low temperature range, maybe this is I would say a reliable assumption, but in a larger temperature range, maybe for a specific component, the CP is maybe vary. There's going to be a variation in CP because CP is a function of temperature, right? So how can we include those things? How can we include those variation in CP in our simulation? So this is where this Aspen Energy Analyzer have option for you to segmentize your process stream uh, such that at this particular segment, temperature segment, this stream, for example, H1 stream, will have a specific CP value, and for another temperature segment, a similar process stream will have a different CP value. So how can you do that? Okay, why this is important is because you want your simulation to be as accurate as possible, right? If you use a constant CP value for a certain temperature range, yes, you will get result, but maybe you have done, maybe there's an overestimation or underestimation on the energy recovery as well as the utility usage or heat exchange area that is required, something like that. So it's better for you to have that in mind, whether you whether you want to I would say, you know use a constant CP value, or you want to segmentize each CP value for each temperature, I would say, interval. So how can we do that? Let's say, for example, H1 here will have a temperature, will have a different CP value for between from one temperature interval to another temperature interval. For example, so if you want to include those cases, right, what you can do is just double click this. Now this what is called, this window will pop up, right? So right now between 170 to 60, right, the MCP value is this one, 1080 to the power of 4. Okay, let's say for example between 170 to let's say 100, right, the MCP is maybe 1000, 1 to the power of 1 to the power of 4. No, wait, 1 10 to the power of 4. All right. Between 100 to 60, they are 1.08 to the power times 10 to the power of 4, something like that. So how can I do that? It's quite simple. If you click here, you have insert segment, right? So you insert segment. So between 170 to 100 Celsius, you can include a different MCP. Let's say, for example, this is maybe 1.1 e to the power of 4. I don't want to change the value too much, but this is how you can do that. So, and then automatically from 100 to 60, you have another MCP. This is where you want to, where you can also include the possibility of having MCP value, different MCP value at different temperature interval. And then you can simply close. Now, when you close, you will see that the segment here is will have symbol, meaning that you have segmentized your hot stream according to a specific temperature interval. But anyway, so that's pretty much how you want to input your process stream. So what are the thing that we can do here, right? Okay, the first, this one I already mentioned doesn't work. Not saying doesn't work, doesn't active, not active. We already do that manually. So if you have information from Excel, you can just transfer data from Excel. So in this case, you can open target view. We haven't specified our target yet, so later maybe. You know what? Might as well just do it now. Okay, the next thing that you need to do is you need to specify utility stream, because you cannot just simply use process stream to heat to get to the final temperature, final hot temperature and final cold temperature. You need to have a utility stream to make sure that everything achieve the target condition. So in here, click utility stream. As you can see here, they will tell you hot stream is insufficient, meaning that okay, if you rely on the process stream, it is insufficient to satisfy the the heating requirement. Same goes with the cold stream. Cold mean that the current process stream is not sufficient to provide the necessary cooling requirement to achieve your target, something like that. So to set your utility, just go to here, and then you're going to use medium high pressure steam according to the what is called, according to the design problem. Okay, again, you can change any of this. You can change cost if you want. Just double click. You can change this condition, whatever you want. But I'm going to keep it default value because that's what is mentioned in the process in the design form. The next one is a cooling. What is called is a cooling water. So these are cooling water. Again, this is okay. This is enough. Now, as you can see, the red one, they turn into a green one, meaning that, okay, if you specify this, the process stream along with the cold and hot utility will be sufficient to complete your, to achieve your target final condition, if you will. Now, I'm going to go back to process stream. Before that, I just want to highlight one important thing that I would like to highlight here is, as I said, you are currently creating a new case. Okay, you have option to switch from the case to a project to convert this case into a project by clicking this one. I don't want to do that, but you have option to convert the case into a project. So no need to worry if you click case first, but actually you don't need to worry if you accidentally click case, you have input everything, but actually you want to create a heat integration project. Don't worry, you don't have to do from scratch one more time, just convert to HI project. All right. Let's see. The first thing that I want to show based on this information and the utility information, you can see that if you click here, this is the heat integration hand diagram, heat integration network diagram, a grid diagram, sorry, where you have your cooling water, your cold utility. You also have your hot utility below. The rest here is your hot stream and then cold stream. Hot stream is from going from the left to right. Cold stream is going from the right to left. Now you have option here to change the okay, this one is hand diagram property view. Just what are the information that you want to provide. Oops, I have 10 more minutes. I don't know whether I have time or not. Let's see. Okay. This one is to show and hide pinch line. Okay, this one later, I will show later. Okay, this one is switch stream direction. This one is to switch stream direction. Just now is from left to right, just to switch from right to left, nothing new. The rest here is we will do this later, okay, on the second part of our tutorial. But this is the grid diagram for your process stream. But in our case, we're gonna create a composite curve, right? So composite curve, just click here. Okay, this is your composite curve. So I make it bigger. So this is the composite curve from hot stream and cold stream. With the pinch temperature of 10. Okay, let's see how can I make it smaller. Oops, I need to close this. All right. Okay, that's the composite curve when you use a temperature difference of 10. Okay, what if you want to use a pinch temperature of 5, right? Yeah, but before that, I would like to explain. In this case, HTC transfer coefficient, you can always adjust according to the information that you have. But in this case, I'm just going to keep it default. Now, DT here is your temperature difference. Uh, Now, as you can see, they are global, right? Meaning that the temperature difference of minimum temperature difference of 10 applies to all. It's basically global, but you can have a specific temperature. Okay, you can have a specific DT for certain string. But I'm not going to do that. Let's see. Okay, how can I change the DT, right? What you can do is just go to utility stream. Oh, sorry. You can go to here, open target view. So as you can see here, you can change DT minimum from 10 to 5 degrees Celsius. All right. Okay, this one is a heating requirement, cooling requirement, area target. Target area here is the ideal case. Ideal case for the best design, I would say. Utility target, as you can see here, heating target, range target, blah, blah, blah. I'm not going to go into details. Maybe this one later, I guess. But there's a lot of things that you can play around. But anyway, so let's say you have changed the utility, the what is called the target DT minimum from 10 to 5, just close, and then you can create the hot composite curve. Now, as you can see, it's become much smaller. So we're going to analyze this composite curve and as well as the earlier composite curve. All right. I think that's pretty much it on how to create a composite curve. by changing the DT, minimum pinch temperature from 10, in this case, 10 and 5. So we're going to analyze what is the cooling and heating requirement when we do that. All right, I'm not going to analyze them here because I already have everything in my Aspen Plus. So let's go back to my Aspen Plus, all right? No, sorry, let's go back to my PowerPoint presentation, all right? All right, everyone, as you can see, this is our Aspen design problem. I think we have covered all. The only thing that we need to analyze is our composite curve result. So we have created a composite curve when we use a delta T minimum of 5 degree, 10 degree, and what we need to do is just compare heating and cooling duty requirements. So let's check out our result. Okay, this is the first solution. The first thing that I want to highlight here is figures on the left, top left. This is just a process stream that you input in your Aspen Energy Analyzer, nothing new. As I said, you can pretty much change your heat transfer coefficient. You can you can provide segment, okay, for each of your stream to account for variation in CP, heat capacity, specific heat capacity, as a function of temperature. If you have that information, and then DT global here is just a temperature difference. The one, the figure on your bottom right is your grid diagram. As I told you, grid diagram is just a diagram showing all of the process stream as well as utility stream on a horizontal line, and they also include their process condition, and they put them on one single diagram. That's it. Now you might be wondering why the process stream, cool and hot stream, are dashed line as opposed to the continuous line. The reason is quite simple. It is because we haven't solved anything yet. Okay, we only provide this and we haven't do any heat integration. Once we do heat integration, and then the program calculates everything, and then everything checks out, any requirement, any requirement has been satisfied, any heating requirement and cooling requirement has been satisfied, no error whatsoever, everything will become a continuous line to indicate that we have solved our heat exchange, heat integration problem. Now, the last thing that I want to highlight here is our target. Now, this is the target when we use pinch temperature of 5 degrees Celsius. Okay, I don't want to talk about number of unit targets, area targets, cost index target, pinch temperature target. We do that later. But the only thing that I want to highlight here is energy target. As I told you, Aspen has several definitions when it comes to target. The first one is they refer to idealized version of the design, something like that. And then the ideal version of the design. But in this case, energy target here means utility. So in this case, heating targets is heating utility. So as you can see, when you set pinch temperature of 5 degrees Celsius, you don't need any heating utility. So you don't need any steam, but you need a cooling. You need to provide a cooling around 1.45 to the power of 10 to the power of 5 kilojoule per hour to do the cooling job, but only for DT of 5. Now I want to remember that 0 and 1.44 to the power times 10 to the power of 5, and how it related to 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 the composite curve. So let's check out our composite curve. Now, this is our composite curve. Okay, this one I just simply estimate based on graphically, but the program will calculate for you. But I just want to highlight where does it coming from. This is the solution. This is the composite curve. When we use delta T, minimum of 5 degrees Celsius. Now, as you can see, this is the recoverable energy between the blue line from here to here. Recoverable energy, okay, from between a hot stream and cold stream. Now, this one is the cold utility requirement. So this additional utility cooling duty need to be provided by your cooling water, and it is 1.4 to the power of 5. Now this is done graphically. It's not really accurate, but it is close enough, because if you remember earlier, it's 1.44 to the times 10 to the power of 5, but this one is 1.4 to the power of 5. So it is between here to here. Now, from the blue line all the way to the red line, it is recoverable energy that we can recover back by exchanging heat between the hot stream and cold. And then lastly, they actually, when you do hot utility, this is lined up this is lined up perfectly. So there are no hot utility requirement. But I just want to show you that it is a small value. So this is where you get the number 0 and 1.45 to the power of. I'm not saying this is how the program do it, but if you want to know how can you calculate how can you get the utility requirement, hot and cold utility requirement. This is how you do it graphically. The one on the left is cold utility requirement. The one between here is the hot utility requirement. And then anything on the right is the hot utility requirement. The one in between is recoverable energy, right? So let's check out the. Okay, as you can see, this pinch temperature, the gap is very small because it is 5 degrees Celsius. Now we check the other one where we set delta T minimum is 10. This become much larger, right? Now when this become much larger, cold utility requirement become bigger. Same goes with this one. From here to here, it is around 6 to the power of 4 kilojoule per hour. So recoverable energy is between here and here. So what's the conclusion from this? Okay, the first thing that I would like to point out here is if you set a minimum temperature approach like really small, you can recover a lot. The recoverable energy is big, and your cold utility becomes small as well as hot utility. But you pretty much suffer in terms of like capital costs, because you probably need a big heat exchanger and stuff like that. But if you make it bigger, your recoverable energy becomes smaller, shrinking, but the utility requirement for hot and cold become larger. So that's pretty much the relationship between delta T minimum, energy target, and then stuff like that. All right, I think that's pretty much all from me. I hope you like the videos. If I said anything that is wrong, please let me know in the comment section. I will try to upload part 2 and part 3 of the videos maybe next week. No, next 2 week, and then a month after that. No, and then 2 weeks after that. All right. What else? Yeah. Provide me with your comment, and I will see you guys in the next video. All right. Okay. Bye and have a nice day.